This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So first, just a few things about midterm tests. Again, apologies for the repetition. It turned out that the error was on our side. It was just one of the settings was just set wrong. I mean, and that prevented you from downloading equations and pictures in the first midterm. So the second midterm went without major issues. One thing that I could observe is that this year you overall did a bit better than in the previous years. Whether this is due to lots of questions being released in the first attempt, perhaps, I don't know. Maybe you are just better cohort, so you just study better, more. In any case, a number of people still failed or obtained poor marks. If you are in that category, definitely you need to start studying harder because there will be more and more material and the exam is not too far. I saw initial sort of dates for, proposal for the exam. So it will be probably early in the examination period. So you won't have much time, after the semester finishes, if these days don't change. So I really urge you to study. Now, if you got a really good mark, but you simply, perhaps talk to your colleagues and just learn how to do those questions that you were lucky to get, then you didn't get good feedback on how you're doing this subject. So the exam is still 70% of the total mark. So this is if you really didn't study and you sort of I shouldn't say cheated, but sort of got assistance, you did not get then an appropriate feedback on how well you are doing. And as I said, the exam is still 70% of the mark. So I urge you again to study. Everyone who hasn't been doing that already, please do that. You won't have much time after the semester is finished. So you will be taught with lots of material in a very short time, so I urge you to study. All right, so that's that. We will now talk about the last lecture on sort of transfer functions, Laplace transform. I want to revisit sensitivity transfer functions as a good bridge towards all the frequency domain methods that we will start from tomorrow. So tomorrow we are starting a total new set of tools. Like we will be presenting frequency domain analysis and design. And talking about these sensitivity transfer functions is a very good introduction to these methods because you will see that in frequency domain we will think about how to shape sensitivity functions indirectly by shaping the open loop transfer function. You will see that just concentrating on open loop transfer function, compensating that object, will give you sort of a tool to kill several birds with one stone. So you can really affect sensitivity and complementary sensitivity transfer functions in one go. So we will learn how to do that when we learn about body diagrams and compensation in frequency domain. But this lecture is really a nice bridge between all the Laplace sort of tools and all the frequency domain tools. All right. So yeah, I was first motivated, as I usually do, motivate this material. And then I will formally introduce this concept of internal stability. So internal stability is something that I mentioned before, but I did not formally define it. I mentioned what it is, but in this lecture we will formally define it. And then the second part of the lecture I will spend some time interpreting sensitivity and complementary sensitivity transfer functions, and through these interpretations we can perhaps conclude what properties these functions should have to have a good design. By the way, typically you would be able to shape these transfer functions through controller design, and then we want to, through this analysis, say, all right, if sensitivity has this property, then design is good. If complementary sensitivity has this property, the design is good, right? And then in the rest of the subject, we will learn how to achieve these properties through controller design, systematic controller design. And then I will wrap up with conclusions. So, if you design any control system, typically you would want all the sensitivity functions to have certain properties. Now, the minimum you would ask from your design is that all four sensitivity transfer functions are proper. So why is this the case? Well, you might design a system, if one of these sensitivity functions is not proper, it's not physically realizable. Mathematically you found a solution, but physically you can't implement it. It doesn't make sense. So properness of these sensitivity functions guarantees physical realizability of your control design or controller, right? And then the second minimum sort of requirement that we can ask is that all four sensitivity transfer functions are stable or Bible stable. And we will say that the system is internally stable if all four sensitivity functions are stable. So internal stability means exactly this. All four sensitivity functions are stable. So now, obviously, this is just a minimum you would require in your design. You might require also some steady-state errors, right? That you may want to have zero steady-state error. You might want to have certain overshoot requirements, certain rise time requirements, etc. But this is the minimum you would ask of any design. So in this lecture, we want to spend some time talking about both of these things, right? So we will see, for instance, how to achieve properness of all sensitivity functions. And we will also talk a bit about this internal stability. You will see that you can check internal stability by simply checking by using a single characteristic polynomial. We call it nominal characteristic polynomial. And basically if all solutions, zeros of this polynomial are strictly negative real parts, that will be enough to guarantee that all four sensitivity transfer functions are stable. So you will have a simple test using a single polynomial, right, for checking internal stability. So what can happen, and that's interesting, we will actually spend a bit of time on this, is that that condition that we will use would preclude any unstable full-zero transformations. I will explain that a bit later. All right. So, by the way, when we check stability, in this subject, we will present three main methods. Two of them we already talked about. So polynomial-based, you look at roots or zeros of a polynomial. So all roots need to be with strictly negative real parts, or poles of a transfer function, it's the same. We also looked at root locus, right? So by the way, for polynomial-based condition, Raoult-Hurwitz is a general test. You don't need to compute roots, right? But you can still check that they satisfy the condition you want. And then the last stability criterion is so-called Nyquist stability criterion. We will present this in the second part of the subject when we cover frequency domain methods. So this is still to be covered. All right. in today's lecture, we want to look at, it's really polynomial-based method, but we will be concentrating on this internal stability, which means all four sensitivity transfer functions are stable. So we first need to remind ourselves what are the sensitivity functions. So let's just look at the top equation. So we consider basically how output of the system Y is affected by all inputs. Inputs are the reference signal, and then input disturbance, output disturbance, and measurement units. Right? So they are the four inputs, and we are looking at the output. So you can show, and this is what we did earlier in the subject, that these sensitivity functions that appear in this equation are given by these equations. Each of these can be obtained by setting all inputs but the one that you are considering to 0. So for instance, you set R non-zero and all other inputs equal to 0, and then you would be able to get complementary sensitivity that relates reference input with the output, right? So that's how you just apply algebra block diagrams with this single input, single output system. You set all the other inputs to 0. And you can keep going. You can set, let's say, R, Di, and Dm to 0 except Do, and then you use algebra block diagram to get SO, etc. So that's how we calculate these guys. Each time you use algebra block diagrams. Now, what we will introduce in this lecture, this is a very important object, this G0C, which is the product of the transfer function of the plant and transfer function of the controller. We will call this open loop transfer function. We often use this notation lambda 0, which is the product of G0 and C. G0 being the transfer function of the plant, and C is the transfer function of the controller. So, why this object is so important? Well, in our frequency domain analyses, this will be the object that we will be playing with most of the time. But in this lecture, also this object becomes very, very important for reasons I'll explain in a moment. So what is internal stability? Internal stability is that each of these transfer functions is stable, right? So that's what we mean by internal stability. Okay. So to satisfy, one of the things also that we said is important for design is that all of the sensitivity transfer functions should be proper for physical realizability reasons. And the first thing we will show is that there is a very simple sufficient condition for satisfying this properness. So we can look at the open loop transfer function. So to satisfy this properness condition, in other words, all sensitivity transfer functions are proper, it's sufficient that the open loop transfer function, which we just introduced, is the product of the controller and plant transfer functions, that this is strictly proper. What is strictly proper and what is proper? Well, strictly proper means that there are more poles, strictly more poles than zeros in the transfer function, and proper means that there may be the same number of zeros as poles. That's what, so relative degree 0, right, that's proper, right? But strictly proper would be relative degree 1 or higher, if you prefer the language of relative degree, right? So here is an example. So if you have a plant which is a single integrator, and you have a controller that is just a proportional controller, right? The open loop transfer function then is K over S, relative degree is 1. It is strictly proper. There is one pole, 0 zeros. So if you just plug in now this, these values of G0 and C into the sensitivity transfer functions, note that some of these are proper but not strictly proper. So sensitivity in this case is proper but not strictly proper. There is 1, 0, 1 pole, relative degree is 0. So, but this is still okay. So you can see now that, you know, in an example, this condition, if open loop transfer function is strictly proper, then all sensitivities are proper, holds in this example. It is actually true in general, and we won't prove this fact, but you know, this is a simple way to verify one of the conditions in your design. So you want to have this strictly proper open loop transfer function. Right? All right, the second condition is a bit harder to check, right? So if you consider this previous example, so in that example, if sorry, K should be positive. Sorry, so this is a typo. So all sensitivity transfer functions are stable if K is positive, not negative. So sorry about that. So because then the poles of each of the transfer functions are, you know, negative, right? So the negative real part. Why is this hard to check? Well, you know, when you look at the open loop transfer function, well, the plant is an integrated controller, is just proportional controller. But what could happen? What could happen is that, note that you might have zeros appearing in some of the sensitivities. And what could happen is that you might have pole zero cancellations. You may have sometimes zero at the same place as the pole. And that really makes this issue a bit tricky. So we want to see what happens, you know, if we have these pole zero cancellations. Actually, what we will prove is a condition that gives us one test for internal stability by looking at a single polynomial. And to prove that that's the right test for internal stability, we will need to look at pole zero cancellations in the analysis. So we will do that next. So to do this very carefully, note that we can write typically plant transfer function as a ratio of two polynomials, B0 and A0. And we can assume that the controller is also a ratio of two polynomials, P and L. So what is the statement that this is the condition for checking internal stability is that if this polynomial here, which we call nominal characteristic polynomial, if this polynomial has all roots with strictly negative real parts, then the system is internally stable. In other words, all four sensitivity transfer functions are stable. Right? So what's interesting about this condition is we are using a single polynomial to check stability of four different transfer functions. So, and the condition here says it's if and only if. Now note that what I did assume is that the plant is strictly proper and the controller is proper. In other words, controller is allowed to have relative degree 0, but I am assuming here that plant is strictly relative degree 1 or higher. So why is this? I want to satisfy the physical realizability condition. I want to ensure that all sensitivity transfer functions are proper, and that was already sufficient condition. We saw that, right? It's sufficient condition for that. And then under these conditions, then just checking roots of this polynomial gives you a test. So if you apply Raud-Hurwitz criterion to this polynomial, and you find that all its roots are restricted to negative real parts, then the system is internally stable. Right? So it's a very simple test. Now, what we want to do next is we want to show sufficiency and necessity of this statement. So note that this if with double F means if and only if. It means that this condition is both necessary and sufficient. What does this mean? If this condition holds, then the system is internally stable. If this condition does not hold, so some roots are with 0 real part or positive real part, then the system is not internally stable. So that's what this if and only if means. This is a really like a crisp test for internal stability. And again, you see here, you can use Raud-Hurwitz criterion to test internal stability. You just have to consider this polynomial. So let's look at this now, both sufficiency and necessity. So how do we check sufficiency? Well, if I write out complementary sensitivity, input and control sensitivity, if I write them out as transfer functions that are ratios of two polynomials, but I express those polynomials in terms of the original polynomials for the Planck and controller, you get these formulas here. So note that in all of these, the denominator is the same. The denominator is the same, right? So you know that A0L plus B0P is appearing in the denominator, all of these. So, and that's exactly our nominal, characteristic polynomial, right? So what does this mean? Well, if this nominal characteristic polynomial has all roots with strictly negative real parts, then indeed all of these 4 transfer functions, 1, 2, 3, 4, they would all be stable in the sense we defined earlier. All poles of each of these different transfer functions are with strictly negative real parts. So sufficiency is quite straightforward, right? Now, what is a problem with necessity is what's the nice thing about this result is it turns out that the internal stability precludes unstable pole zero cancellation. So what I mean by this, let me just explain. So suppose that you have a Planck and controller transfer functions where you have that controller has this unstable pole at 1, right? Which is chosen exactly to cancel this 0 at 1. So there is an unstable 0 in the Planck, and that's cancelled by the unstable pole in the controller. So what is perhaps temptation that you might want to consider here? Temptation would be to cancel this unstable pole and unstable 0, and then work with this open loop transfer function. However, if you do that, that will, you're making a mistake. First, if you look at what you need to work with is you need to really proceed as we described earlier. You first need to find all of these sensitivity transfer functions using these formulas, right? So if you did that pole zero cancellation, or let's not do it just to see what happens. So if you just keep that pole and 0 as they are, it will turn out that in at least in one of these transfer functions, unstable pole would appear in the denominator. And there won't be actually cancellation in the sensitivity transfer function, whereas you had a cancellation in open loop transfer function. So let's look at that. So if you keep this pole and 0 uncancelled and you plug these guys into formulas, these formulas are correct. These formulas here are correct. So we just identify what is B0, A0, P, and L. We plug them into these equations, which are correct. And those are the correct equations for each of the sensitivities. If you do that in this example, you would find that in the input sensitivity, this unstable pole appears, whereas in all others, it was not there. So this is an interesting thing. It's like a structural thing, which basically says that canceling these two guys and then trying to find sensitivity, well, you would be losing information. The correct way of doing it is, well, use the original PL and B0 and A0, plug them into these formulas, and then see what happens with poles and zeros, right? It turns out in the example, well, this unstable pole here would pop up in at least one of these sensitivities. Now, this can be actually proved in more detail. Right? So that actually leads us to basically the proof for necessity. But note, in this case, what is still true if you consider a nominal characteristic polynomial as defined in this slide here, right? Then you would find that nominal characteristic polynomial is equal to this. And now you just have to work with that polynomial. There is an unstable root s equal to 1 is a root of this nominal characteristic polynomial. So the test that we proposed is correct test, right? And when we look exactly at what each sensitivity transfer function look like, well, these guys are stable, but one of them is unstable. Know that internal stability requires that all the four sensitivities are stable at the same time. Right? So in this example, one of them will not be stable. Right? So resist this temptation to cancel these guys and then work, right? Because that's and actually the condition we presented really prevents you from doing that thing, because the test is basically necessary and sufficient. So what we want to do now, we want to analyze this sort of situation from the example in some sort of proof that shows necessity of the condition. So we are basically saying, well, if the system is internally stable, or if the polynomial, if all four polynomials, transfer functions are stable, you would have that nominal characteristic polynomial will be with negative little parts or roots. So this all has to do with pole zero cancellation now. So what we are now analyzing is just a slightly more general formulation of that, what we saw in the example. So we have that controller and Planck transfer functions are given by these polynomials, and what we are saying, well, suppose there is a pole zero cancellation, so there is some, so how can pole zero cancellation in open loop transfer function can happen? Well, we might have that A0 has the same root as P, right? So there is, the same, so we can factor out this S minus P from A0, and we can factor out the same element in P. So we here assume P is positive just to have this unstable pole zero cancellation. So if you now just plug in these sort of assumed polynomials into output sensitivity, well, it turns out that P would cancel in the output sensitivity. But if you look at the input sensitivity, you just plug it into the formula with our assumptions, you will see that S minus P remains there. So what this tells you is, if there was a possible pole zero cancellation in the open loop transfer function, which is the product of C and G0, well, that pole zero cancellation would somehow pop up in one of the sensitivities, right? So it won't cancel. These things won't cancel in at least one of the sensitivities. So which is, in this case, this is what you get. So in other words, P does not cancel in input sensitivity, and hence, you would not have internal stability, right? If you cancel this unstable pole zero. You can do the other way around. So now you can say, suppose that we have that L and B0 have pole zero cancellation. Now what we are saying is that this guy and B0 have the same root, right? And again, unstable. Then you can again find that P would not cancel in the input sensitivity. So this sort of shows you that this condition that we presented is necessary and sufficient. All right. So in other words, it precludes this pole zero cancellation. All right. So going back to the condition, I just want you to remember that in order to check internal stability, basically stability of four sensitivities at the same time, you have to come up with this. You have to write down, find this nominal characteristic polynomial, one polynomial, and then test where its roots are. If all roots are with negative real parts, they are in the left half plane, you have internal stability. So that's the condition that you need to use. And then the proof basically is just sort of providing extra intuition information about how this works. All right, so are there any questions regarding the test for internal stability? Yeah.
Excuse me, I have a nominal characteristic polynomial with all negative real parts, but the plant is over, not strictly over. What would happen?
Look, we didn't. First, you might not. So if the plant is proper and controller is proper, you might not get properness of all sensitivities. So even at that step, physical realizability is not possible. Right? You can't realize such a system, right, with physical components. So that's what might break down. Right? So what we are doing is we are assuming strictly proper plants to, and proper controllers to ensure physical realizability. If the plant, obviously there are plants that are just proper, but then you will need to choose controller that is maybe strictly proper, right, in order to ensure physical realizability. Right. So, but why we are sort of stating it this way, we just want to have a general result. I'm stating one result. There is an equivalent result where you would say, well, if plant is proper, but controller is maybe strictly proper, right? Then, as long as you tick off physical realizability, you would have a similar test, right? All right. So, the next thing that I want to talk about is a very nice introduction to frequency domain methods. We will keep coming back to some of these things that I will state here, show you here in the rest of the subject. So what I want to do is, well, I want to basically concentrate on sensitivity S0 and complementary sensitivity T0, and give them some interpretations, extra interpretations, which would be helpful in terms of intuition, what they mean, and also they would be guiding us in designs. And lots of frequency designs would follow this intuition that we will sort of explain now. So let's look at that now. So we want to first consider sensitivity transfer function. So sensitivity formula for sensitivity transfer function or output sensitivity. So by the way, sensitivity is given here, and that's the relationship between DO, which is output disturbance, and the output Y, right? So you may ask yourself, why the name? Where does the name come from? So I want to explain a little bit about the intuition behind the name, and that has some useful consequences that we will use for design later on. So there are two possible ways to understand why we call this object, this transfer function, sensitivity. First, we can look at the error in open loop versus error in the closed loop. And then there's one sort of way to interpret this transfer function. And another one is to look at plant uncertainty and how feedback loop affects, how it can handle plant uncertainty. So what I mean by plant uncertainty, you have a model that's not correct. There are some parametric, uncertainties in your model. Well, can the control deal with this, and in what way? So sensitivity, the name really comes from this transfer function really capturing both of these things in a nice way. So I will explain that next. So let's first look at error in open loop versus error in closed loop. So what is the error in open loop? Well, think about controller transfer function which is equal to 0. What this means, well, I basically open the loop. There is no more closed loop because this guy is 0. So U is, just 0, right? Because of that. But I can still talk about the difference between the output and reference, which is my error in open loop. Suppose I want my system to track some reference, but I have open loop control. Right? So if you compute what error in open loop is as a function of all the inputs into the system, you will get something like this. Right? So this is algebra of the block diagrams. I'm not going into details, but I'm just explaining the steps. If you now assume that control transfer function is non-zero, we do have a closed loop, right? So we have some sort of closed loop. And if you calculate now the output with a closed loop, so the error, so the output is given by this, and then the error is again difference between Y and R. So if you do all the calculations, you get this formula. So what you can see from this formula, which is error in open loop, and this formula, which is error in closed loop, that the ratio of closed loop error and open loop error is exactly equal to the sensitivity transfer function. So now you can see, all right, that's algebraically interesting, right? So fair enough, but why do I care? Why do I care? Well, if you can make, so obviously sensitivity is a function of a complex variable, but I can still talk about small s0 if I look at maybe magnitude of s0, right? So if s0 is small, that would mean that the closed loop error is made smaller by the controller. So because of the controller, because of the closed loop, right, we basically are getting better tracking. So the smaller the S0 is, the better the tracking we have, the better tracking of references with closed loop controllers. Right. So you can think about this as, you know, sensitivity of the error with respect to the closed loop structure of the system, right? So this is one way to interpret it. So I still haven't talked about what does this small mean. Well, when we start looking at frequency domain, we will represent things with body diagrams. If you remember body diagrams, they will have a magnitude part and phase part. Well, magnitude small would mean what I mean here. This S0 small would mean in magnitude over different frequencies, right? We will come to that later, but this sort of, just think about this small S0 is good for tracking of references, you know, as a sort of general statement that should sort of lead your intuition. And later on we will use this as a design guideline, right? And we will do that systematically using frequency domain methods. Here is another interpretation. So what I'm doing here is I'm basically saying, let's look at the object now. I'm not giving you precise calculation, you know, of these steps. So this is what this means. This D of GCLO, so that means GCLO is a G transfer function for the closed loop. Now, what does this D mean? Well, this D means if I perturb it slightly, if I look at the small difference between some nominal closed loop transfer function and some, you know, true transfer function. So it's like a differential, but differential in this object, which is transfer function. And I look at the relative. So dGCLO over GCLO is like a relative error due to perturbations in the model, right? In the closed loop. And I do the same, but then I just look at the perturbations in the plot, right? So if I look at that, you can show that this object here is equal to this object here, which is exactly, again, it's shown in some books, you know, Flecking with Powell Rogata will have calculations like this. So it's again equal to the sensitivity transfer function. Now, why is this significant? Well, note that again, small sensitivity implies that the closed loop plant is less sensitive to changes or modeling errors than the open loop plant. So basically, by closing the loop, we are making the system less sensitive to any sort of modeling errors. If you look at plant modeling errors, and then you look at modeling errors in the closed loop with a controller there, well, small sensitivity guarantees that the closed loop really helps a lot. Right? The smaller the S0 is, the more the closed loop helps in dealing with plant uncertainty. If you remember operational amplifier example, which we presented as motivation in this subject, we said that the closed loop there, you know, was used to deal with uncertainty. And that's exactly the situation here. Closed loop did manage to make S0 small in that example. That's exactly where the feedback was useful, dealing with uncertainty in the plant. All right. Now, if you look at the other transfer function, the other sensitivity, complementary sensitivity, if you look at the error, right, which is basically r minus y, y minus r, you can find that it is equal to this minus this. Now note that what you have here is that measurement noise is multiplied by complementary sensitivity. So if complementary sensitivity is large, then the noise will affect your error, the tracking error, a lot. So obviously complementary sensitivity small is good from the point of view of the sensitivity to measurement noise, right? So because if I'm multiplying a dm with something that's small, well, that would have small effect on the error, and I want this tracking error to be zero if I can make it. Right? We are usually interested in steady state error zero, for instance, right? But the effect of measurement noise on error is given here, and it's through this complementary sensitivity, and then we want this guy to be small. Now, where is the catch? So we are saying sensitivity should be small, we are saying complementary sensitivity should be small, but you have to remember that the sum of sensitivity and complementary sensitivity is always 1. If you look at the formulas for sensitivity and complementary sensitivity, transfer function, so note that if I add this to that, at the bottom we have the same thing, and on top we will generate the same thing. So basically this sum is always 1. No matter what G0 and C you use, the sum of the sensitivity and complementary sensitivity is always 1. So what does this mean? Well, it's a tricky thing. We are saying S0 should be small, we are saying T0 should be small for different reasons, but then the sum should be 1. It can't happen, right? So you can't satisfy this always, but there is a catch, which is a trick that is fortunate for us. It turns out that these disturbances, output, input, and disturbance, and also references, are usually largest at low frequencies. So these are sort of slowly varying signals, perhaps. And measurement disturbance is largest at high frequencies. So think about measurement noise as something that really varies quickly, right? And has high frequencies, right? And usually small amplitude. So what we can do is, and this is where frequency domain methods are invaluable, we can make S0 small at low frequencies so that we satisfy this condition, S0 is small at the frequencies that matter, right? And then we make T0 small at high frequencies, at frequencies that matter. Because T0 would only be, if you look at here, well, DM is a high frequency signal, so then the question is how much would T0 amplify DM, which is at high frequencies? Well, we will learn how to analyze this using frequency domain methods. But this sort of algebraic constraint, which is always there, can be overcome by, having this sort of seesaw thing. So for small frequencies, we are making S0 small, and then T0 is maybe close to 1 even. And then for high frequencies, we'll be making this guy small, and then S0 would be maybe close to 1. Right? Now, note that you need to remember that if I take the magnitude of S0 and add it to the magnitude of T0, that's not the same as magnitude of S0 plus T0. Right? The magnitude of S0 plus T0 is 1. We just said that. So because left-hand side, right-hand side is the same, right? So, but note that this is not the same thing. So although we have this, in general we won't have that. And this is relevant for frequency domain methods. If you think about these now as magnitudes in body diagrams, right? Well, you won't expect that the sum would be, 1, although this algebraic constraint holds. Right? Sorry? They could be what? Sorry. Complex numbers. Well, it's think about even real numbers, right? If you look at, even if they were real numbers, if I wanted to say what is the absolute value of S0 and how can I relate it to the absolute values of individual components, you will have some sort of triangle inequality, right? Think about S0, so forget about this constraint, but let's just talk about that inequality there. So if S0 is 1 and T0 is minus 1, then the absolute value of the sum is 0. That's 0. But if I take absolute value of minus 1 and absolute value of 1, there is an inequality. I'm saying that this inequality here, does not rely on S0 and T0 being complex functions of S. It does not rely on that. Even for real numbers, you won't have equality. And the example is S0 is minus 1, T0 is 1. Then the absolute value of this is absolute value of 0. But then if I take absolute value of 1 and absolute value of minus 1, I get absolute value of 1, absolute value of minus 1, that's 2. So 2 is greater than 0. That's the only thing you can say, but it's not equal, definitely not equal. All right. So by the way, this sort of analysis is very useful to guide your intuition in a lot of designs that will come later in frequency domain, because we will be trying to achieve small t0 at some frequencies. We will try to achieve small s0 at other frequencies, and these will be our design guidelines. Now, how small we want to achieve, that will depend on our design specifications. So every new example you deal with will have a set of specifications. And then from that set of specifications, you will say, well, at small frequencies, I need to make S0 so small, and such a small S0 would tick off my specifications. And similarly, specifications will tell you how small T0 should be at some other frequencies. We will learn how to do that systematically in frequency domain methods. And this is a very nice introduction to that material. All right. So what we did today, we presented condition for internal stability of a closed loop system via roots of a nominal characteristic polynomial. So that's a very cool result. You just learned now how to check yet another stability property, internal stability, still using Raoult-Hurwitz. Because you write down the nominal characteristic polynomial, apply Raoult-Hurwitz, and you have your test for internal stability. And then we also presented several interpretations of sensitivity transfer functions, which I believe would be invaluable for what comes next, which is frequency domain methods for analysis and design. All right. Are there any questions? All right, I'll see you tomorrow. Thank you for your attention. See ya.
Just now is if it is the negative feedback, right? So the x0 and t0 would be the positive and all less than 1.
Positive and less than 1.
Yes, x0 and t0. If it is negative feedback, right? So the equation holds. The equals holds.
I don't see it.
If it is a negative feedback, right? If it is a negative so the C0 and F0 right? If it's a negative feedback.
Well, no. In case of negative feedback, we consider T0 plus S0 is always 1.
Yeah.
Some is equal to 1, not pure 1. It's equal to 1.
They are positive, separated. They are positive unless they were.
Not necessarily.
They're all positive.
I don't think you can talk about them being positive.
Okay, they might be negative. It's what I mean. The C might be negative.
Right. I mean, look, just think about it.
Okay.
Control of transfer function can be -1.
Oh.
And
And the
plant
plant can be
-1.
okay.
Right. So I don't understand. Yeah.
就是说